Welcome class to our Krusty Krab hash map training video for assignment 6. And for this assignment, we're going to be creating our own custom hash map. And then we're going to, in main, create a menu sort of driven program to emulate an automated sort of payment ordering system. Now, of course, Mr. Krabs didn't like this in earlier episodes of SpongeBob, but, of course, he has to adapt his business model. And of course, there was a lot of bad reviews about Squidward running the front register and taking orders from customers. But of course, we're going to still preserve somewhat the essence of Squidward in the ordering system just because, well, we're still kind of just used to Squidward, of course, handling all the orders. Okay, so let's go ahead and first go talk about the actual custom hash map structure we have to implement for this assignment. Okay, so this is going to be our hash map class, and of course we're going to have our two templates, class T1, T2, because of course for a hash map structure, or really any search structure for that matter, always has to have a key value. So you search by key and retrieve the value associated with that key. So pretty much that's why we have these T1 and T2s right there, and here is our complete class. So right there we have this struct key val. So the purpose of doing this is because every entry in this hash map is going to be a key value pair. So of course we have our T1 key and T2 value. And feel free to actually create any constructors for this struct if you want for this struct key val, which actually I did in my program. I did a constructor for this, but it's up to you. So this structure is really going to be an array of linked lists. So it's going to be using that separate chaining mechanism to store the entries. But we are going to have sort of a hybrid with that with open addressing. So you notice this static const int right here in my program. So this is going to store the value 5, which means that there can be no more than 5 nodes in each of the linked lists in our table. So our table is a vector of linked list where each element in a linked list is a key value pair. So we can't have more than 5 at each spot. Now, of course, I will draw this out a little bit more in detail so you can get a nicer idea of how this has to look like, but that's what this represents. Then, of course, filled entries, that's going to count how many entries in your table contains 5 nodes. So, for example, if table at index 0, if that linked list contains 5 nodes, then you increment 1 to your filled entries. So we're trying to store how many filled entries we have in our table. So essentially, we can't have more than 5 nodes. If one element in our table, if one of the elements, one of those linked lists has 5 elements, we have 1 extra filled entry. That's the whole idea. Now our hash function is rather a simple one. So actually it's going to return just sort of a number. Now, of course, we're going to, I'll show you right here. Okay, so these 2 lines of code right there is all you have to really use in your hash function, I guess. So we're going to create a variable of type hash, which is in C++, and we're going to call its parentheses function operator, pass in the key, and it returns some random, some big value. But as always, for the same key, it returns the same value every single time. So this is going to be just our simple hash function. So the whole purpose of having it separated like this is because, well, if we were to have multiple hash functions for this hash map, let's say, we can easily overload this hash function for different types and be able to call different sort of hash functions, or we can create different hash objects for different types. So this way it makes it a bit more easier to, I guess, maintain, or it's a bit nicer this way. So that's why we have it separated like this. So anyway, that's your hash function. And then the resize function, well, you're going to resize by an amount. So let's say, for example, if your table contains 5 elements, and I pass in 5 into the resize, then I want to resize my table by adding 5 more elements to my table. So my table, which was 5, if I pass in 5 into this, then my table is going to be 10 elements. And of course, remember, resize has to remap everything from the older, smaller table to the bigger table. And then we have our default constructor. All this constructor will do is it will set this filled entries value to 0, and it will resize this table to be 5 elements. That's all it does. So I think I have the code right here for you. So let me just make sure it's here. Tell you right there. So there is the first part of the code, and here's that second part. So 2 lines of code right there. Now, of course, the bulk of this assignment is going to be this operator bracket function. So you're going to pass in a variable T1, so some type of key of type T1. Now, in our assignment in main, we're going to actually create a hash map. We're going to map a string to some custom type. The value will be a custom type. So what happens is we search based on the key and return that value by reference. So this bracket operator is going to insert if this T1 does not exist in the table, or it returns just the value of the node without inserting if it finds an existing matching node in our linked list. So let's go ahead and just sort of talk about exactly how this operator bracket is going to work. So here is our hash table, our structure within our hash map object. And right now we're going to focus just on the keys. So those numbers or those names there in red are going to be keys, or I guess they're names in this case. We're not going to focus much on the value fields because the value is, well, whatever you want it to be. We're going to focus just on the keys for right now. So in this table, we can see here that we actually have 5 elements at that topmost linked list. And that means that this index 0 of table is a filled linked list, because we don't want to have more than 5 in any of the linked lists in this structure. So we have the filled entries set to the value 1 in this case. And we notice that all the names are sorted. So you want to have a sorted linked list. Now, actually, this structure is a bit wrong, because if you're using the list in STL, it's actually doubly linked list. But we'll just sort of focus on the fact that we're not going to do too many. I guess we might do some backwards reversals. But anyway, for now, this will be a simplified version. But really, it's a doubly linked list behind the scenes with that list class. So we can see here that our linked list is sorted by keys. We have so in our first table, we have Abe, Jen, Ron, Stan, and Zach. They're sorted from the front to the end. And our last linked list, we have Abby, Beth, Danny, and Erica is also sorted by name. So you want to maintain a sorted list by always inserting into the correct spot. Now, what I don't want you to do, I don't want you to do a push back and then sort the list. I want you to actually just simply insert it. So as you're linear traversing through a linked list, I want you to find the location where the element has to go and use the insert function for the list class to insert a new node in between, or between any 2 nodes in the linked list. Now, it could be at the beginning or at the end, but if it does belong in the middle, don't just push it to the end and sort. Just make sure you insert it into the correct sorted position. So as always, the way this bracket operator works is we're going to call the hash function. So let me go ahead and sort of write the prototype, or the actual function sort of definition over here. We have T2 operator, or T2 ampersand, sorry. And then we have hash map T1, T2 operator bracket T1 key. So of course you have to call that hash function. So I actually gave you this code in the handout. You can of course going to just say hash function. You can use the key and then mod it by table dot size. That's going to map you to a position. So let's say, for example, back in main, in my brackets, so the same way you would call this function, the same way you would call it like you do for unordered maps that we've already done earlier. So in main, you have your hash map object, you use the bracket operator, you pass in some string into that bracket operator. Let's say for right now, let's say we get the name Jerry. I don't know, so let's say Jerry for right now. So I want to insert Jerry into this structure. So I'm going to put this right here. I'll put this here below. I'll insert insert or find Jerry, should I say. Now, of course, in this case, Jerry is not in our table, so you have to find Jerry. Let's say let's say index I happens to give us the value 0. Let's just say, I'll put this here, let's say I is going to be 0. So let's say I take the hash function and pass in Jerry, it returns some value, modded by 6, happens to give us the value 0, let's say. Then you want to go ahead and search this linked list. So I believe in the PDF I give you some pseudocode, but of course you're going to use an iterator. So of course you can use the auto type right now, and now remember table 0.begin returns the iterator of that first node in the linked list. Then of course you search this linked list and you try to find Jerry. So in this case right here, since we can assume that this linked list is sorted, we first look at the name Abe, and Jerry is not equal to Abe, so we move over here to the next element. And then we have Jen is not equal to Abe. Sorry, Jen is not equal to Jerry. My mistake. We're looking for Jerry and Jen is not a match. We go to this node right there and we see Ron. So at this point right here, we can stop looping, because we know that if Jerry is in this list, you would have already found it by now. But the fact is we actually went from Jen to Ron. That means if Jerry did exist, it had to have been somewhere between Jen and Ron. So you can stop right there. We already know that we obviously could not have found Jerry in this list. We have to insert Jerry into this list. Okay, so let's look at this index 0. Well, there's actually already 5 nodes in this table. So if that's the case, we have to linear probe and go to the next index of our table. So we're going to try index 1. Index 1 is blank. So then, okay, we're going to go ahead and insert Jerry right here actually, because we see that this index 1 is an empty list. So just insert Jerry right there. Just make sure I get this all nice. So here we are. Good enough. And then we're going to just write the name Jerry right there. And we're going to use, so we have to also set this node's value field. So we set that node we just created right there. We set the key field to be Jerry. And we're going to set the value field. Well, I think I have it in a PDF, but we're going to use T2 to set this new node's value field. Remember, this T2, this right here is going to just really be a default of whatever type value is. So if value is integer, it will assign a 0 to the value field. If T2, if it happens to be maybe a custom type, it's going to use that default constructor value or default constructor object to set the value field of that node. So that's how that works. Now, of course, let's go ahead and do some more insertions. So we first inserted Jerry into this list. Let's go ahead and now insert, I'll just say maybe Cam. Let's insert Cam. So insert / find Cam. Let's say when I have Cam is my T1, this key parameter is going to contain the string Cam. Remember, when we call this operator in main, we simply, the same way as we called it using our unordered map, the same way we're going to use this. We're going to go ahead, you call bracket operator, pass in the string between the brackets, and then in this parameter in this function body, key will contain the string Cam. Let's say if I take this hash function and pass in Cam, modded by table size, let's just say for right now it happens to give me the value 5. Let's just say, just to make things easier. So this hash function with Cam, modded by table size will give me 5, let's say. Okay, so we have to go to index 5. And of course, we're going to call table index 5.begin, which will give us the iterator that points to that first node. So the iterator is the same way it works like with assignment 1, except here we don't have to create our own custom iterator. It's sort of given to us in that STL list. So we check. So Abby is not equal to Cam. So we try next element. Beth does not match Cam either. Now we see Danny right there. So, well, the fact is that, if we see Danny right here, that means Cam doesn't exist because Cam had to be before. So Cam had to have been between Beth and Danny. So that means that we can already conclude right now that Cam is not in this list. So we check this list actually is not maxed out. So you want to go ahead and insert Cam between Beth and Danny. And you can actually use the insert function that's kind of built into the list class. And it requires you to pass in an iterator that tells the list class where you want to insert the elements. So you call insert, you pass in the iterator. So iterator is like that pointer. And then, of course, you pass in the value you want to insert to that. So, of course, what's going to happen right here is when we insert this new node, we have to set the key and value field for this node. So, of course, each node in this linked list is going to contain a key value pair struct. So, of course, you have to dereference the point. You don't dereference the pointer just yet, but you may have to at some point. But the idea is you have to just simply call insert, pass an iterator, and then pass in what you want to assign to this. So, of course, you want to assign Cam and T2 to this new node. So, of course, you call insert, and the result is going to be just you're going to create this node right here. And of course, Beth will point to this node will point to Danny. And you have to essentially pass in a value. You're going to pass in basically a key val struct will be passed into this, where it's going to contain Cam, and it will contain some T2, some type of default T2 value, using the T2 sort of parentheses like this. So we'll just call insert, and it will magically insert this node into the linked list. And of course, you have to pass in the value. So there we are. Now, of course, once you do that, you see here, after we insert, we have to check right away, do we have 5 elements in this linked list? And we do have 5 elements in this linked list. So we have to increment our fill entries by 1 at this point. And then, of course, we return that value field in that node that contains Cam. And of course, then we're done with this function. So let's say if I want to go ahead and find Stan this time around. Now, I'm not going to go over the whole detail, but right now we see here that our load factor now, we have 2 filled entries and we have 6 elements. So 2 over 6 is 1/3. We're going to be over 20%. So we have to, once our filled entry divided by our table size is above 20%, we have to resize. Now, I'm not going to do that right here, but you have to, write the code. You have to sort of, write the resize function, and of course it'll get called at this point. So we actually do call, if we do again use the bracket operator to insert or find the name, let's look at Stan. Then of course the hash function with Stan modded by table size will give us the value 0. Now, before we even look up Stan, the first thing we'll do in our bracket operator, we first check our load factor. If it's above 20%, which in this case it would be, resize your table. But since I'm not going to go over the resize, let's just say for right now that we don't resize, but you're going to have to write the code that will do this. But of course, you check and then you call resize in the bracket operator if needed. But let's say for right now, resize, and we have this just to make things simpler. Index 0, we check. We see is not Stan. Next element, not Stan. Not Stan. Oh, we found Stan right there. So return the value field automatically, and that's it, you're done. So essentially, we have to use table index i.begin that returns an iterator of the first node in that linked list, and we just linear search that linked list once you find either that node or we find that gap where, okay, like for example, like when we tried to insert Cam between Beth and Danny, there was actually, if Cam was to exist, Cam would have been between those two, but since we jumped from Beth to Danny, that means we know Cam exists between those two, so we call the insert function and pass an iterator, and we had to pass in a key val object as well. So in this case, we found the existing entry, so we just simply return the value. So I think I might have over exaggerated this explanation, but that's how this works. And of course, using the STL, using that list and vector makes life a lot easier. So for the resize function, well, I'm not going to give out the code for it, but just like in class, all you have to do is go through every entry in this table, and we have to create a bigger table. So in that resize function, you're going to essentially pass in a value, an amount. You want to resize a table by this amount, and then you have to remap everything from this table right here to a new location in the bigger table. So there's not much of I think the rules are relatively simple here, but what you want to do is just be careful with some of the remapping. So in main, when we're going to actually be using this hash function, so there'll be certain moments in main where we're going to be searching for some type of an item, and this item does not exist in our hash table. Unfortunately, it's going to create this entry regardless. So you only want to map elements that are not sort of, I guess, dead weight in this hash table. So back in main, we're going to be using the bracket operator to do search. On a failed search, then this bracket operator returns some default value back, which tells us in main that it was unsuccessful. But unfortunately, it does create the entry in the table, which is okay, but we don't want to remap that failed search to our new larger table. So you want to check and make sure we only want to map elements where the value field is not a default value, if that makes any sense. So that way, when we have to remap, we check that value. If it's default, then don't remap that to the bigger table. Only remap elements where the value is quote unquote not a default. It contains some valuable info, I guess you can say. But again, you have to kind of figure that part out. But that's really about the bracket operator and the resize function. So hopefully this part right here helped you out. So now I'm going to go ahead and go over the main part, the input file, and also do a demo run of the program. So let's go ahead and get to that part. So before I go into the main algorithm, I want to first go over data structures needed as well as the input file. So you'll be provided input file in this program where every line contains one menu item. So each line is broken up in the following way. We have a string that denotes the item's name. Then we have a double, which is going to be a decimal value, which will store the price of the item, then followed by an integer that will store the quantity of the item in that store. And of course, we use a space to separate them, and every line ends with a new line character. So you have to populate your hash map with all of these. So if you look back in the PDF of main, or sorry, of the PDF provided, you have basically a hash map where you map a string to a menu item. So you're going to use this string. So for example, fried oyster skins, who can forget that from that episode from SpongeBob? So we're going to map this string to a struct, and the struct will be called menu items, and the menu items contains these two fields. It contains a price and a quantity. So you map a string to a struct that contains a price and quantity. So rather not so complicated to store and retrieve the items. Now on top of that, you also want to have a vector of strings. You want to store the names of all of the menu items. And the reason why is because in main, we have to output the complete menu. And you want to make sure that we output them in the same order as they were read in, or you want to output them in some particular order, because for code grade, if you don't do like that, it can cause problems. So now we didn't implement an iterator for the hash map. If you were to have done that, then the problem with that is then there's all kinds of orders. Remember when you iterate through a hash map using the iterator to retrieve the first and second fields. Remember that? How they're not always in the same order whenever you output them in one program, in one environment versus a different environment. So we want to make sure we have all of the names in a vector, so we store them in a particular order, so we always output in this same order every single time, so that way it becomes less of a problem for code grade. So okay, so I think that kind of clarifies that. Let's go ahead, and now I'm just going to actually not really go over the PDF for main, but rather just do a test run right here so you can see how it's supposed to work. And of course, I'm going to provide a test run in the PDF. I'm going to again give you a list of input files you can use. You can use input redirection to sort of test with multiple inputs. I'll also give you the output that I generated also using output redirection. I'm going to use those same input outputs to test on code grade. Let's go ahead and just now go into the simulation of this program. Okay, so I'm going to now just do a demonstration of this program. So just like with assignment 1, we have a header file, hashmap.h, that contains our class declaration and implementation in one file. We include that in our main file, and then we have to just only compile the main.cpp file. So let's go ahead and do that first. Let's run this. And of course, the first thing we do is we ask for an item, or ask for the items, the file that contains our items. So menu items.txt, and displays our complete menu. And again, we store all of our menu item names into a vector. The purpose so that way we output them in the same order we read them in, so that way it will match everything on code grade. And of course, for price and quantity, we simply just use the name of the item to map it and to return the struct that contains a price and quantity amount, which we output to the screen. So that's how we use that. Now, of course, after we output the entire menu, Squidward will of course ask us ask us for an item, or ask us to order, but of course in a very unpleasant way, as always. So I'm going to actually first order a diet Dr. Kelp. And then it actually finds this element in our menu. So we're not going to linear search our vector of names. We're going to use this string diet Dr. Kelp to use with our bracket operator. We're going to pass this string into it, and it retrieves back a menu type object, which contains $2.99 for its price and 20 for its quantity, which means that it found the element. So if it didn't find the element, it will still insert it into our hash map, but then it returns a default menu type object, which tells us that it was not successful. But in this case, since it returned not a default, but an actual, valid menu type, that means it was successfully found. So we use this hash map to retrieve, not linear search anything. So of course, I'm going to enter 5 of them. So I want to read 5, or I'm going to order 5 Dr. Kelps. Okay, and of course we have another pleasant message from Squidward. Then we ask if it will complete the order for the user, and I'm going to type N for no, so we want to keep ordering. We display this menu once again, and then of course we see for the diet Dr. Kelp, let's see, there it is. We have 15 quantity, not 20 anymore. So I'm going to go ahead and just test this out, that we want to make our search case insensitive. So when I go to enter, let's say, diet Dr. Kelp like this, well, it's not going to be the same exact sort of casing. The upper and lower case characters are a little bit off, but it has to still find everything. It has to still search and find this. So we enter, it does find the element again. So now let's enter an amount. So it is 15 total in our store, or in the Krusty Krab. So if I enter, let's say I want to order 20, it will sort of prompt me to try again, because 20, we don't have actually 20 in supply. If I enter, let's say 17, again, it will keep on re-prompting until I finally enter a valid amount. I'll just try 2. So I'm going to order 2 sodas now instead. And there we are. So also, before I go ahead, every time we do an order, we have to also keep a running total. We have to maintain. So we've so far ordered 5 sodas earlier, then 2 sodas now. So 5 times $2.99 plus 2 times $2.99. We add those up. So of course, we're going to not end our order. We're going to keep on working with this. So now that we do have our Diet Dr. Kelp, let's go ahead and order a pizza. So for that one episode from SpongeBob where they, Squidward and SpongeBob go through all this trouble to deliver a pizza to this customer, but they forgot the Diet Dr. Kelp and the customer went crazy. At least now, if you order a pizza, we safely do have our Diet Dr. Kelp, so we can go ahead and just order a pizza now. So I'm going to go ahead and order a pizza. Again, it finds it. We look up. We use this pizza string for our bracket operator. It returns back a menu type object that's not going to contain defaults, so we know for sure it was a successful search. I'm going to order one of these. I only have one of these at the store. Again, I'm not done with my order just yet. So now, after I ordered a pizza, so from earlier we had one pizza on the menu, but now if you go to our menu again, we see that we don't have a pizza anymore. We're missing one because since we ordered one pizza, there's 0 of them, so we don't want to output that element to the menu this time around. So that's also another thing we have to also account for. So if there's 0 of them, then don't output them. So in fact, if I were to actually enter pizza again, so pizza is found, but since the quantity associated with pizza is 0, Squidward is going to give us a very nice message once again. We serve food here, sir. Okay, fine. So it found it, but unfortunately there are 0 quantities, so it doesn't exist in the menu. So that means it doesn't exist. Therefore, it's not food, I guess. There we go. Now, also, if I were to, let's say, type in Dr. Diet Kelp, then it's not going to find this because, again, this element does not exist in our menu. So when we do a Dr. Diet Kelp like this, it will not find an existing entry. So it's going to actually create a new entry in our hash table, but the value associated with it will be set to a default. So default will tell us in main that, oh, that means this element was just created, therefore it wasn't in the menu earlier, therefore it doesn't exist. We serve food here, sir. Now, if I were to again do this, Dr. Diet Kelp like this, it will again return we serve food here, sir. Even though this time around it's going to actually find the existing entry, but because our hash map assigns default values to our entries, it's going to return a default value once again, which denotes that it doesn't exist. So just to kind of, make sure we're aware of that. Now, of course, I'm going to order one more thing. So, of course, we have to order a Krabby Patty. Without that, we're not really, it's not a true visit to the Krusty Krab. So let's order a Krabby Patty. And I think there's 50 of them in the store. Yes, so I'm going to go ahead. I'll order like 20. Okay, and now I'm going to be done with my order. I'm going to hit Y. It ends it. It outputs the complete order. And I use IOmanip to make sure it outputs to 2 decimal places, but it's a very simple, IOmanip feature. And of course, we get a very nice send off by Squidward. So, essentially, that's how this program works. Now, also, I'm going to provide you with some input files. So I'm not going to have inputs given to you in PDF, but I will provide you with input files you can use. You can use Linux input redirection to be able to read that input, so you can just sort of test your program out if it's working correctly. I'm also going to provide a set of output files that are also generated using output redirection with the redirected input file. And of course, all the files I'm going to give you on Canvas to test will also be used in CodeGrade as well. Now, also remember on the PDF, make sure that if, let's say, we have no more items at all left. So I'll have one input test that will have nothing. So after you order everything, nothing in the restaurant left, the program also has to end. So it ends if the user enters Y to complete the order, and also it ends if the program, if we're out of menu, or out of items. Every element in our list is all 0 for the quantity. Obviously, we bought everything that was, at the Krusty Krab. So it's also, that logic is also given to you in the PDF as well. So other than that, I guess hopefully this video did sort of help you get an idea of how this program is done. So I guess happy coding. As always, stay safe, and until next time.